Okay, so last time we started talking about greedy algorithms, and today we're just going to continue that. So remember, the idea in greedy algorithms was that I'm going to make a greedy choice. I'm going to do whatever looks good at the moment, and I'm going to hope that in the end, these greedy choices, these locally optimum choices, lead to a globally optimum solution. But then every time we get algorithms that are quite simple, so our algorithms were one line, but we had to go back and prove that they are actually correct. And the proof of correctness was the part that was actually harder than the algorithm itself. And generally speaking, the way our proofs of correctness worked was that I said, suppose someone else gives me an optimal solution, which is different from my solution. I will just take a bunch of steps to turn the optimal solution into my solution. And I show that these steps do not make the solution any worse. They don't increase my cost. And that shows that my solution is also optimal. Or another way of looking at this is that whenever my algorithm is making a choice, for example, let's say here when I'm doing the sorting, basically every time I'm choosing to put the shortest possible file, right? So I can say every time that I'm making a choice, if I can prove that there is at least one optimal solution that makes the same choice, this would prove that this choice that I'm making is not removing any of the optimal solutions from the set of possible outputs of my algorithm. And if all of my choices are like that, then of course, at the end of it, my algorithm is outputting an optimal solution. You can look at these proofs in both ways. They're literally the same. But today we're going to see some other problems, and we're going to try to solve them using greedy algorithms. So I'm going to start with the problem of giving change, which is probably a famous problem. I hope that some of you at least have seen it before. So let's say that you're implementing a vending machine, and this vending machine takes in coins and also banknotes, but only gives out change in coins, right? And let's assume that you have in coins of every type. So there's no limit on how many coins you have. It's just that in the input, you're going to get some number K. And this K is basically the amount of money that you have to return to the customer. So the customer has bought something, gave a banknote, you have to now return K dollars, right? And in the output, you have to basically show how you can return K dollars. So let's say that I want to return K dollars. And for now, let's assume that the coins that I have are denominated as $1, $5, and $10. So those are my coins. So let's say I have $1, $5, and $10 coins. So in the output, I want you to give exactly K dollars, but I want you to use the minimum possible number of coins because people don't like to get a lot of coins, right? So if I'm just going to return $10, I would return one $10 coin. I wouldn't give them 10 $1 coins, right? So pay these K dollars with the minimum possible number of coins. Okay, so this is what I want to do. And generally, okay, if you look at it as a program, I can say that my output either says how many coins are needed, or it just gives the list of coins that I'm going to give. Now, you can decide. So my output can just be the number of needed coins, or it can just be an optimal list of coins. And by optimal, I mean, of course, as short as possible. Let's do the second one, because if I'm doing the second one, then you can just take the length of the answer and just say that's the number of needed coins. Okay. So what's the first greedy algorithm that comes to your mind here? Any ideas? So it's very simple. Try to pay as many $10 coins as possible. And only when the remaining amount is less than $10, try to pay with $5 coins. And only when the remaining amount is less than $5, try to pay with $1 coins. So this is a greedy algorithm because every time I'm paying the largest possible coin that I can pay. Okay. So this is my algorithm. And again, my algorithms are always very simple. It just says, as long as K is positive, as long as I have to pay something, just check. If I have to pay at least 10, if K is at least 10, then print a 10 or output a $10 coin and decrease K by 10. Otherwise, check if K is greater than 5, greater than or equal to 5. If so, then just give a 5 and decrease the amount that you have to pay by 5. And finally, otherwise, you just print 1 and you decrease the amount that you have to pay by 1. So that's the algorithm. Now, why is this algorithm optimal? So in other words, why is it that if I can pay a $10 coin, I would never pay a combination of $5 and $1 coins? Because actually 10 is a multiple of both 5 and 1, right? So this means that I would never have two $5 coins in my output. Because if I have two $5 coins in my output, I can always replace them with one $10 coin, right? So this is again the same as before. I'm saying, suppose someone gives me an output and that output is optimal. I'm going to prove that that optimal output is going to have at most one $5 coin. Why? Because if it has two $5 coins, I'll just remove those two and add a $10 coin. And this is a better output. And it's a contradiction with optimality, right? Now, I can do this because 10 is a multiple of 5. But 5 is also a multiple of 1. So I can do the same thing with my $1 coins. I can say I have at most 4 $1 coins, because if I have 5, I can just take these 5 and put a $5 coin instead. And that's enough. Basically, if you can just prove, as we did, that I'm going to use at most 4 $1 coins and at most one $5 coin, it means that if my K is greater than or equal to 10, I'm paying the 10. Because if I don't, I cannot do it with only one $5 coin and four $1 coins, right? And the rest of it is very simple. Okay, great. So we see that the greedy algorithm works if I have coins of these denominations, 1, 5, and 10. But this argument went through because every denomination was a multiple of the previous one. Let's say I add a $2 coin. Okay, so this is my question. What if I have these coins? I have 1, 2, 5, and $10 coins. Would a similar algorithm still work? So, I mean, by similar, of course, I mean that I'm just adding another else in between, and every time I'm just paying the biggest coin that I can pay, right? And it turns out, even in this case, the greedy algorithm works. Okay, so greedy works. But why? Well, I mean, 10 is a multiple of all of the other ones, so the same argument as before works for 10. If I can pay a 10, I should pay a 10. And also, like, 2 is a multiple of 1, 5 is a multiple of 1. The only problem I really have is with 2 and 5, right? So because 2 is a multiple of 1, I know that no matter what, I'm going to pay at most one $1 coin, right? Now, here's the thing. Would I ever pay more than two $2 coins? It is possible. So for example, if I want to pay $6, just pay three $2 coins, right? But you're already seeing that's not optimal, right? So if I have three $2 coins, I can take them out and replace them with a 5 and a 1. So without saying that 5 is a multiple of 2, I could still argue that I'm going to use at most two $2 coins, right? But I'm also going to say I will never have two $2 coins and one $1 coin, because I can just take all three of them out and put a $5 coin in, right? And this argument basically shows that every time I'm going to just take the largest possible coin, and it's going to be optimal. Okay. Let's really make this break. What if I have, let's say 1, 2, 5, 8, and 10? Would the greedy algorithm work now? So, I mean, a more general question can be, would the greedy algorithm always work no matter what kinds of points I have? No. Okay, give me an example here where the greedy algorithm would not be optimal. Yes. Yes. So if I want to pay 13, my greedy algorithm would pay 10 first, because that's the largest thing that it can pay. And now it wants to pay 3, so it pays 2, and then it pays 1. So this is 3 coins. But of course, 13 is just 5 plus 8. So I could pay it with 2 coins. So in this case, greedy fails. And this basically shows that whenever you're using a greedy algorithm, it's really important to prove that your algorithm is correct. And the correctness of the algorithm can depend on a lot of parameters. In this case, if only I just change my coins, a correct algorithm suddenly becomes incorrect. But okay, for now, we just want to solve this problem. So how would you solve this? I cannot use the greedy algorithm, but I can use a variant of what we call dynamic programming. And this session is not about dynamic programming, but I'm just going to give you the algorithm for this one problem. And the idea is this. Let's say that I just create an array, and I say that I want the case element of my array, so AK, to be the minimum number of coins needed to pay K dollars. Okay. Now, I want to fill out this array starting from index 0 and just going forward, right? So I have this array. Let me actually just write the code or pseudocode here. It's super easy. So I say for every K from 0 to whatever, some number, to let's say, I don't know, some N, I want to calculate AK. Now, what is A0? And remember, I have these coins. I have 1, 2, 5, 8, and 10. If I want to pay $0, of course, I don't pay anything. So I don't need any coins. So A0 is 0. So that's the first thing I do here. I say if K is 0, then AK is 0, and continue. Okay. Now, otherwise, if K is not 0, I want to pay K dollars, I have to use some coin, right? So I can say, well, I'm either going to use a 1 or a 2 or a 5 or an 8 or a 10 as the first coin that I'm giving out, right? But if I pay out a 1, then I have to pay k minus 1, right? But in ak minus 1, I already know how many coins I need to pay k minus $1, right? So my answer would just become 1 plus a of k minus 1, if I know that I'm using a $1 coin as my first coin. If I use a $2 coin as my first coin, it would be 1 plus a of k minus 2, and so on. And of course, I want the optimal solution. So I'm going to take the minimum of all of these, and I'm going to use the combination that uses that minimum. So all I say here is that AK becomes the minimum of 1 plus a k minus, let's call it j, where j is either 1 or 2 or 5 or 8 or 10. Okay. And by the way, in this minimum, if some of them don't exist, for example, if my k is 4, of course, I don't have k minus 5. So I wouldn't take those in my minimum. Right? This is pseudocode. I'm not going to write it in more detail, but this is now my algorithm. Now, what are our runtimes? So what is the runtime of this greedy algorithm? Well, it's okay, right? Because I have to basically just print all of these things. And if k is a multiple of 10, I will literally pay k over 10 different coins. So it's going to take okay. Can I make this faster? If instead of printing all the coins, I just want to count how many coins I need, can I make it faster? Well, yes, because I can do this. I can say, let's have a count, which is the number of coins that I want to pay. And then I say, while the amount that I have to pay is greater than 0, let's first check if I want to, let's first just check how many tens I'm going to pay, right? And let's pay all of them together, right? So actually I can remove the while completely, and I can say my answer increases by k over 10, because that's the number of $10 coins that I'm going to pay, right? And after I pay this, of course, I have to do this. So I just have the remainder of k by 10, and that's what I have to pay now, right? Now, again, I do the same thing with 5. So I say I want to pay k dollars. How many $5 coins am I going to pay? K over 5, right? And then k just becomes the remainder of k by 5. And then do the same thing. Well, I mean, I didn't have a 2 here. I just had this. So I just say my answer increases by k at the end because my last coin was a $1 coin. Okay. So I can also do this. And what is the runtime here? The runtime here is constant. Right? Because I'm literally doing a constant number of operations. Now, this was about the runtime, but how much memory am I using? So let me take this and put it on this side. So how many units of memory am I using here? You see, I'm not really allocating any new memory. I mean, yeah, I have this variable k that I'm working with, but that's constant memory. And here I have this CNT and k, that's also constant memory. So both of them are using O1 memory. Okay, so I can run these programs on machines that have very little RAM. They don't use much RAM at all. Now, how about this one? What is my runtime here? Let's say based on n. Again, I'm just going from 0 to n. So that's n plus 1 iterations. And in every iteration, I'm doing a constant amount of work because I'm creating a constant size set. This set has size 1, 2, 3, 4, 5 at most. And I'm just taking its minimum. So that's a constant amount of work. So my runtime is O(n). Okay. How much memory do I have to use? Well, I need this array, right? And because I'm saving this whole array from 0 to n, my memory is also O(n). Now, you can reduce the amount of memory usage here. Because if you just stare at this long enough, you realize that when you are calculating AK, you only need the values of AK minus 1, K minus 2, K minus 5, K minus 8, and K minus 10. So instead of keeping track of all the values in the array A, you can always only keep track of the last 10 values. And that's always enough for you. So it is possible to reduce this memory usage to O(1). But at the end of the day, my runtime here is linear. My runtime is actually not only O(n), it's literally theta n, right? So my runtime is linear, whereas here I could have constant runtime. So if the greedy algorithm works, I prefer the greedy algorithm. But unfortunately, the greedy algorithm doesn't always work. So I always need a proof to see whether the greedy algorithm works or not. Here's what I want you to consider. Suppose that you have a really long text, and let's say that it's written in some alphabet. Let's say it's written in the English alphabet. It has 26 letters, and all of them, let's say, are lowercase. And you want to save this long text into a file. Now, the problem is that, of course, the files in a computer, they use bits. You have 0 and 1, right? So you have to somehow translate your letters of alphabet to zeros and ones. And that's what we call coding. Okay. So a code is basically very simply a function, C, that takes the letters of your alphabet and maps them to strings of zeros and ones. So this is the set of all strings on zeros and ones. And sigma is my alphabet. So let's say let sigma be a finite set, which we call it alphabet. And in my case, sigma is just, let's say, the letters in English. Now, of course, a code is only useful if I can decode it. So I want to save it to a file, and then I want to be able to read the file back, read that sequence of zeros and ones, and reconstruct the same message that I originally had, right? So I think you've already heard about the ASCII code. So the idea in the ASCII code is that we take all of the letters that we want to represent, and we basically give each of them a sequence of zeros and ones, a sequence of numbers in binary. Okay, so for example, here, yeah. So A would be represented by the number 41. No, that's in X. Okay, in decimal, sorry. Yeah, A will be represented by the number 65, right? And in binary, this is how you write 65. So that just gives you a sequence of zeros and ones for writing the letter A. Now, of course, B is 66, so you have this sequence of zeros and ones for B, and so on. Now, generally speaking, in ASCII, our sequences always have the same lengths. So the code that we use for every letter is always 8 bits, 1 byte, right? So this is a little bit problematic, of course, as all of you know, because Chinese has more characters than you can represent here. That's why we have things like Unicode. But I mean, if you have many characters, you can just make the code words longer, right? So that's actually what Unicode does. So instead of having 8 bits, you can have as many bits as you need. You can have the log of the number of characters bits. Okay, but there is another problem here. If I give the same length of code to every character, my files actually become really big. Because imagine if I'm writing an English text. In English, there are very few occurrences of the letter X. It doesn't appear very often, right? But there are some letters that appear much more often. For example, E or S, right? But we're giving the same length of code to all of these letters. That doesn't make a lot of sense. It would be much better if I could somehow have a short letter or a short code for the letter E and maybe a much longer code for the letter X. So if I could just represent E with just 1 0, that would be great, because that's the shortest possible code that I can give to a letter. Whereas for X, X is so rare that I would be fine with assigning it maybe 16 instead of just 8 bits, right? So this is the idea that we want to consider here. We want to find kind of an optimal code. But before doing that, I have to tell you how to represent codes and what do I mean by an optimal code. Okay, so the first thing is that I want my codes to be so-called prefix-free. So what is a prefix-free code? I say my code C is prefix-free if the code of no letter is a prefix of the code of another letter. Okay, so prefix-free means that for every 2 letters, let's say A and B in my alphabet, the code of A is not a prefix of the code of B. Okay, so for example, let's say I have just the alphabet A, B, C, D, right? And let's say that I want to assign the code 0 to A. Now all of my other codes have to start with a 1, right? Because if I assign 0 to A, but if I say B is 0, 1, then I have a code that is a prefix of another code. And that cannot be allowed. Okay, so I know that all of my other codes have to start with a 1. Now I want to give a code to B. Let's say that I give B the code 1, 0. Now my other codes cannot start with 0. They cannot start with 1, 0. So they're all forced to start with 1, 1. Right? Back to our codes. So I've assigned code 0 to A, which means that no other code can start with 0. I have assigned 1, 0 to B, which means that no other code can start with 1, 0. So the codes for C and D have to start with 1, 1. Okay? And let's say that I give C 1, 1, 0 and I give D 1, 1, 1. Okay? Now this is a prefix-free code, because you can just check it. Like, just look at each one of these codes. It's not a prefix of the other. Now, the thing that is interesting is that I can have a code tree, or actually later on we will call this a trie when we're working with string matching. But for now, we just call it a code tree, which is just a tree representation of this code. Now, how do I create a code tree? Very easy. I create just one node that corresponds to the empty string. For every node, I say that it can have at most 2 children. And basically going left corresponds to a 0 and going right corresponds to a 1. Okay. So here the code of A is just this leaf. So I'm starting from here, doing 0, that gives me A. B is 1, 0, so B is like 1 and then 0. This is the code of B. C is 1, 1, 0. So I start from here, 1, then another 1, and then a 0. So this is the code for C. And finally, D is 1, 1, 1. So I start at the root, go 1, 1, and another 1, and this gives me D. Okay. So basically, every node here corresponds to the string that is written on the edges from the root to that node. So this node, for example, corresponds to 1, 1. This one is, of course, 1, 0. Now, of course, if you give me a code, I can create a code tree, right? It's very easy. If you give me a code tree, I can create the code. Now, what are the properties of these code trees? Well, the first property is that they're binary trees, right? Every node can have at most 2 children because we only have 0 and 1. But there is a nicer property as well. All of our code words, all of these words are always at the leaves of my tree, right? If you look at A, B, C, and D, they're all at the leaves. And actually, I also don't have extra leaves. My leaves are exactly corresponding to the letters of my original alphabet. Okay. So I'm going to ask you a question. And this is the first problem that we want to solve. Let's say that in the input, I give you the code tree, but I give it to you without the assignment of the letters. Okay. So I'm just giving you the structure of the code tree. Okay. So my input contains the structure of the code tree. Or another way of looking at this is that I can equivalently say that I just give you the code words. So for example, I give you 0, 1, 0, 1, 1, 0, and 1, 1, 1. Okay. Or code words. Because it doesn't matter which one I give you. If I give you the code words, you can make the code tree. If I give you the code tree, you can make the code words. Okay. And let's say that I'm also going to give you my alphabet, and I'm going to tell you how many times each letter is appearing in my text. So imagine that I just want to save a very particular string into a file. And maybe this string is really long. Maybe it's a whole book, right? So I'm just telling you that in this book that I want to save into this file, there are these many A's, these many B's, and so on. Okay, so I give you the alphabet, and for every letter, let's call it A in the alphabet, I also give you the frequency of A. So I tell you how many times the letter A appears in my file, and let's call that FA. Okay. Now in the output, I want you to give me the optimal code. Okay. But okay, maybe it's not correct to say the optimal code. I want you to give me an optimal code because maybe we have many different codes. Okay. So what's going on here? I'm giving you this tree, and I'm telling you this is the structure of the code. But I don't tell you where every letter is going to be assigned, right? So let me just copy this. In the input, I haven't told you where to put each letter. All I have told you is that my letters are, let's say, A, B, C, and D. And I tell you that the structure of the code is this. So this is the code tree. And I'm also telling you how many times every letter is appearing in my file. So maybe I'm telling you A appears 5 times, B appears 10 times, C appears 4 times, and D appears 15 times. Okay. Now you have to assign letters to the leaves of this tree structure. Basically, you have to say which letter do you want to encode by 0, which letter do you want to encode by 1, 0, which letter do you want to encode by 1, 1, 0, and which letter by 1, 1, 1. Right? Now, what is it that you want to minimize? You want to minimize the size of your file when you're writing all of these bits, right? So what is my cost function, the cost that I want to minimize? My total cost is just this. I sum over all letters of my alphabet. This looks really weird, but this is the alphabet. This is a sum, right? I'm just going to take the frequency of that letter times the length of the code that I'm assigning to that letter in bits, right? That's how long my file is going to be. Okay. How would you assign in this example? So I just want you to put A, B, C, and D on these leaves in an optimal way. So here's the thing. I'm going to assign some letter here, and whatever letter I assign here will only use 1 bit of information to be encoded in the final file, right? Whatever letter I assign here will need 2 bits. And this one will need 3 bits. This one will also need 3 bits. So I prefer the letter with the maximum frequency to have the shortest possible code, right? So I would put D here because D is going to appear 15 times, and I prefer to just write 1 bit every time that D appears. Now, among the rest, the maximum frequency is B, so I prefer that B appears here. And finally, I have C and A. It doesn't really matter because both of these have a cost of 3, right? So it's like 110 has a length of 3, and 111 also has a length of 3. So I'm going to put either C here and A here, or the opposite. It doesn't really matter. As you see, we have more than one optimal. Okay. So if I give you the structure of a prefix-free code, and if I also give you the frequencies, you can easily just use a greedy algorithm to optimize it. You say, I take the letter with the maximum frequency, and I assign the shortest possible code to it. And I just continue this. Right? Every time, take the letter with maximum frequency, give it the shortest code. Alternatively, you could do the exact opposite. You can always say, I always take the letter with the minimum frequency, and I give it the longest code. Now, you can prove that both of these approaches are optimal. And again, the proof is very similar to proofs of optimality that we've seen before. You can just swap, right? So suppose someone gives me a code where they've put C here, up here, where I put D, and they put D where I put C. I can just swap those two, and my total cost goes down. Okay. So I can do this kind of proof to show that this is optimal. But this is only if someone gives me the structure. And as we talked before, the structure is basically the same as the code words, right? So my code words here are 0 for D, 10 for B, 110 for A, and 111 for C. So if I either had this tree structure or these code words in the input, I could create my optimal code. I could assign the codes to letters optimally. Okay. But what if I don't have that? What if I don't give you the tree? I just give you the letters and the frequencies of all the letters. And I tell you, find the optimal tree and find the optimal assignment of letters to nodes in that tree. Okay. So this is our actual coding problem. So let's call this problem 2. Did I call the previous one problem 1? No, I called it first problem. Okay, so I have to call this one second problem. in my input, I'm just going to give you the alphabet. And for every letter, I'm going to give you its frequency. I'm going to tell you how many times that letter appears in my string. Alphabet alpha, and for every letter, alphabet sigma, and for every letter A in sigma, I also give you its frequency FA. Okay, this is the input. And as the output, I want an optimal code. An optimal prefix-free code. Okay, so you have to build the tree yourself, and you have to also assign each letter to one of the leaves of the tree. Now, of course, I know how to do it if I have the tree, but the hardness here is that I'm not giving you any tree. I'm just saying find the optimal tree, find the best possible thing. Okay, and of course, what I want to optimize, my total cost, is exactly the same as before. So it's just the frequency of every letter times the number of bits that I need to encode that letter. So let me just take the same inputs that I had here. That's my example. And let me actually add one more letter, or maybe two more letters. So I also add E with frequency 2. And okay, I don't want to add F because then I have to write F of it. Okay, so I have these letters and these frequencies. Here's my algorithm. And well, not my algorithm, Huffman's algorithm. It's a very simple greedy strategy. And it just says this. It says, take the two letters that have the smallest frequencies. In this case, E and C, which have frequencies 2 and 4. And just merge them into one letter. Okay. Then recursively solve it on the n-1 letters that you have. And at the end, just make them into 2 letters again. Okay, so I'm going to show you what I mean, but let me just write it. So it says merge the 2 least frequent letters. Solve recursively. And let's say these 2 least frequent letters were whatever, letter 1 and letter 2. And I merged them into some L bar, a new letter. Okay, I solve recursively, and then I break the vertex corresponding to L bar by adding 2 children. So I do this. I had this vertex that corresponded to L bar. I just add L1, let's say, as the left child, and I add L2 as the right child. This is Huffman's algorithm. Okay, let's do it here. So I'm going to take the 2 least frequent ones, which are E and C, and I'm going to merge them together. So I'm going to have a new letter, let's call it EC. Okay, and this letter, this is just one letter, okay? I'm calling it EC, but it's one letter. And this one will have a frequency of 6, just the sum of the frequencies of the previous ones. Okay, now again, take the 2 with the fewest frequencies. So I have A, which is 5, and EC, which is 6, and just create a new letter. Let's call it AEC. And this one will have a frequency of 11. Okay. Now, again, take the two with the least frequency, so that's B and AEC. Merge them into one, so F of BAEC is 21. Again, take the two and merge them into one. So this is F of, what was that one? D. So DBAEC, and it's 21 plus 15, 36, right? Okay. Now at this point, I'm happy because I have only one letter, DBAEC, right? So if I have only one letter, I know what the optimal code is, right? What is the optimal code for one letter? Yeah, well, just assign 0 to it, right? So I can have this. I can just have one node, and I can just assign 0 to it. I can say this 0 is here, and it corresponds to DBAEC. Okay. But this is not great. In this particular case, I'm going to say this. If I have only one letter, I can just assign the empty string to it. Okay, so I'm going to start with this. I'm going to start with DBAEC being assigned to the empty string. Now, every time I have to go back and break the vertices. So DBAEC, on one side I had D, on the other side I had BAEC, right? So I'm just going to break it down. I'm going to say put D on this side, let's say on the 0 side. It doesn't really matter which side you put it, and put BAEC on this side. Now, again, BAEC was itself AEC and A. So I'm going to break it down. Let's say I put A on this side, and I put, sorry, it was B and AEC, right? Yeah, it was B and AEC. So I put B on this side, and I put AEC on this side. Now, AEC itself was the combination of A and EC. So I'm going to, again, break it down. Let me use another color. So let's say I put A on this side, and I put EC on this side. Finally, EC was a combination of E and C. So I'm going to break it down, maybe like this. And I put, let's say, E on this side and C on this side. It doesn't really matter. When you're breaking down, you can put whichever you want on whichever side you want. So I'm claiming that this is the optimal code. So the optimal code is to assign just 0 as the code for D. For A, I want to assign 1, 0, 0. For B, I want to assign 1, 1. For E, I want to assign 1, 0, 1, 0. And for C, I want to assign 1, 0, 1, 1. Okay. Why is this optimal? So here's the thing. If someone had given me this tree, as in the previous problem, would I assign the letters to leaves in the same way? Yes. Because what did I do in my previous greedy algorithm, which was also optimal when I had this structure? I would just say, take the vertices that have, and take the letters that have the least frequency and put them as far as possible from the root. So put them in the last possible level. And this is exactly what's happening here. E and C were the least common letters, and I'm putting them at the bottommost level here. So I'm giving them the longest possible code. And then I'm continuing like this. So, but this doesn't prove anything. This just proves that with this particular tree, I have an optimal assignment of letters to leaves, right? But maybe someone else can give me another tree looking completely different than this one. And maybe that tree has a smaller cost than this. So I have to prove that that never happens. I have to prove that this tree always has the optimal cost. So this is my proof of correctness. So here's what I would say first. Consider any binary tree, any non-empty binary tree, any binary tree with more than one vertex. It's really hard to say. Consider any binary tree with more than one vertex. Okay. Do you agree that it has two leaves at the bottom level, at least two leaves at the lowest possible level? You can easily see that, right? Because I mean, just do it inductively. I start with just one vertex that has two children, and I have two leaves at the lowest possible level. Now, if I add children for a particular node, I'm going to add two children for it, so I will have two leaves. And this continues. Okay, so any binary tree that I have here, any binary tree that is a code tree, it's going to have at least two leaves at the lowest possible level. Another way of seeing this is suppose that I have only one leaf at the lowest possible level. So suppose that I don't have this leaf here. I only have something like this, right? I could make my code shorter. I didn't need this last extra edge, right? If I didn't have this one, why would I create a tree like this? I don't need this 0. I can just assign 1, 1 to C instead of assigning 1, 1, 0 to C. So whenever I'm taking one node and I'm adding children for it, I'm adding both of its children. And that proves that I always have children in pairs. So if I look at the last level of the tree, there are at least two nodes in the last level of the tree. Okay, so this is the first thing that I wanted to prove, and I just did. So this is my first lemma. I'm going to say the last level of the tree has at least two nodes. Now, what tree do I mean? I mean any tree in the optimal solution or in any optimal solution. So I'm going to say, suppose someone gives me an optimal solution. And let's call that optimal solution, let's call the tree T. And let's say that it also has the corresponding code. Okay, so the last level, the last level of this tree T has at least two nodes. But in the previous problem, I said that I can always take the nodes that have the smallest possible frequency and I can put them at the last level, right? I can assign them the longest possible codes. So I'm just going to use that. So I'm going to say that I look at this tree that someone else has given me, whatever this tree is, this tree T, and I'm going to say that at the last level, there are at least two leaves, maybe more. Now, additionally, I can always make sure that these two leaves are siblings, right? Because I'm always adding pairs of siblings. Has at least two, instead of nodes, let me say two sibling leaves. Okay. Now, in my algorithm for the previous problem, I would assign the two nodes, the two letters with the smallest frequency here. But let's say that this optimal solution didn't do that. Let's say that this optimal solution put the two letters with the minimum frequency somewhere else, right? I can always swap their place. And I can always bring those two letters with minimum frequency to these two nodes, right? And this can only decrease the cost. It cannot increase the cost. Because I'm making, let's say, one of these letters, let's say the letter with the smallest frequency was here in the optimal solution, and I just swap it with this one. What's happening here? I'm making the code for the letter with the smallest frequency longer, but I'm making the code for another letter which had a higher frequency shorter. So overall, my cost is going down. If they have the same frequency, well, my cost would remain the same. Okay. So anyway, this kind of swapping cannot increase the cost. It can only decrease the cost. So I can say I take this optimal solution that someone else gave me, and I swap all of these so that I now have a new optimal solution. So I'm going to say this. I'm going to say after swapping, I have a new optimal solution, new optimal tree. Let's call this new optimal tree T prime. Okay. Now, in this tree T prime, again, let's just draw something here. Let's say that I have these two elements here, and these are the two elements with the smallest frequency. Okay. So here's what I want to ask you. What is the cost of T prime? What is the total cost of this tree T prime and the code corresponding to it? And let's just say that these frequencies are F1 and F2. Remember, these are the smallest frequencies, right? And let's say that my tree has a height of h. Okay. Now, I can just basically go over every vertex, and I can say that the cost, sorry, I can go over every leaf, and I can say that the cost for this leaf is just the frequency of its letter times the number of the level that this leaf is in, right? But I don't want to do that. Remember what my algorithm did. My algorithm would just merge these two leaves into one new letter. My algorithm would just merge F1 and F2 into a new letter that had frequency F1 plus F2, right? So let's say that I put that letter here, right? And then I look at this tree. Okay. I'm going to give this one another name. I'm going to call it T star. So T star is the tree that is obtained by merging these two, or basically removing these two leaves, but giving the sum of their frequency to their parent, which is the operation that I'm doing. But again, remember that this was an optimal solution that someone else had given me. So I'm just saying on your optimal solution, I do this. Now, I can write the cost of T prime based on the cost of T star, right? What is the cost of T prime based on the cost of T star? It's just the cost of T star plus F1 plus F2. Can you see why that's the case? Just think about how many times you're going to go over every node, right? So let's go back here. In this example, I want to print D 15 times. So this edge that is in the path from the root to D, this will be printed 15 times, right? Now I want to print B 10 times. So for 10 times, I have to print these. I have to print this 1 and then this 0. For 5 times, I have to print this 1, and then this 0, and so on. Generally, if I look at every edge of my tree, how many times is that edge printed? The number of times is equal to the sum of frequencies of all the leaves that are children of this edge, that are below this edge. Sorry, not children, descendants of this edge, right? But what am I doing here when I'm doing this operation? I'm basically removing two leaves that had frequencies F1 and F2, and I'm giving their parents the frequency F1 plus F2, right? So if I look at this smaller tree, this tree that doesn't have these two extra vertices, every edge in the smaller tree is going to be printed as many times as it's going to be printed in the larger tree. The only extra edges are these two edges. And this one is going to be printed F2 times, this one is going to be printed F1 times, right? So the cost of my big tree is just the cost of my small tree plus F1 plus F2. Okay. Now, here's the part where things get interesting. I showed that there is always this kind of construction. So no matter how you created this optimal tree of yours, I could always take your optimal tree and I could always, after some swapping, make sure that the two nodes with the minimum frequency are siblings at the last level. And then I could always make sure that the cost of your optimal tree is the cost of this smaller tree plus the frequency of these two nodes, right? Now, so whatever this smaller tree is, this smaller tree has to also be optimal because your big tree is optimal and the cost of your big tree is just some fixed amount, F1 plus F2, plus the cost of the smaller tree. So this means that T star is an optimal tree, right? It's an optimal code tree, but of course it's an optimal code tree for which alphabet? For the alphabet in which these two letters, the two letters with frequencies F1 and F2 are merged into one letter, right? Because if I have a better tree for that alphabet, I can just replace T star with that better tree and I get a better T prime, which gives me a better cost overall. Okay, so now I can just use induction, right? I can just do induction on the number of letters that I have. Suppose that my algorithm always gives me the optimal tree for one letter. Well, I can prove that actually, the base case of the induction. Yeah, of course, for one letter, I always get the optimal tree. For two letters, I always get the optimal tree. Now, suppose that my algorithm always gives you the optimal tree for n minus 1 letters. Now, if I have n letters, the best possible cost that I can get for a tree on these n letters is the best possible cost that I can get on n minus 1 letters plus F1 plus F2. But I know that my algorithm gets the best possible cost for n minus 1 letters. So my algorithm is optimal. Okay. I'm going to put a link to the book that writes all of these things much more formally for you. But I just wanted you to understand how the algorithm works. Now, we have only 10 minutes. I want to quote this. Here's what I want to do. First of all, let's also talk about the complexity. What do I want to do? Every time I want to be able to take two letters with the smallest possible frequency, and I want to merge them into one letter. So what are the operations that I need to do here? I need to always be able to find the smallest letter, the letter with the smallest frequency, sorry. And I need to also be able to remove it. And I need to be able to add a new letter, which corresponds to two previous letters with a new frequency. So I can just do this with a heap, right? In a heap, we had the operations of adding elements and always taking out the maximum element, or if we had a min heap, then the minimum element. So in C++, actually, we have a heap, and the heap is called priority queue. Okay. So here's what I can do. I can say I have a priority queue of integers, and I call it H because it's a heap. But the implementation in C++ is a max heap. So you always have your maximum element at the top. Okay. If I want a min heap, which I do in this case because I always want to find the element with the smallest frequency, I just multiply all of my frequencies by -1, right? And then I use the maximum. So that's easy. Let's say I create a new struct, and basically this corresponds to one node of my tree. What is it going to have? It's going to have a frequency. It's going to have a left child and a right child and a parent, right? I don't need to keep all of these, but I'm going to keep them anyway. And maybe it also corresponds to some character. Okay. If it's a leaf, it will also have a character. If it's not a leaf, I'm not going to use it. Okay. Now, let's say I want to read some text. So I do this first. I read some string S. And let's assume that my string only has characters in the English alphabet. So I'm just going to count how many times each character appears. So I'm going to have a map from characters to integers called count, and I'm just going to count. So I'm going to say for every character C that appears in S, increase the count of C. Okay, I just counted how many times each character appears. Okay, I could also, instead of having a map, I could just say that this is an array of size at most, let's say 300, because C++ by default uses the ASCII codes, so the codes are between 0 and 256. Right? So every character is basically a number between 0 and 255. So I can just count how many times every character was there. And now for every character, I want to create a node of my tree, basically a leaf of my tree. So I say for every I from 0 to, again, let's say 300, if this character appeared, if the count of this character is not 0, let's create a new node. I'm going to call it NC. And this node's, star NC. This node's frequency is just going to be the number of times that this character appeared. The character is the character, right? And it's not going to have a left child, a right child, or a parent. All of those are going to be null. Okay. I don't need to write this, but I'm just writing it to emphasize that they're null. Okay. So now I want to put all of these nodes in a priority queue, and I want to do it in the order of the frequency. But I'm lazy, so instead of creating a priority queue of nodes and then having to write a comparator for comparing different nodes, I'm just going to put pairs of integers and pointers to nodes in my priority queue H, right? And here I'm just going to say in H, push this. So for the frequency, I'm going to use the frequency times -1, because remember, I want to have a min heap, not a max heap. And for the node itself, it's just NC. Okay. So now I have this heap, which basically every element in the heap is a pair. The first part of the pair is the frequency times -1. And the second part is a pointer to the node. Now, what do I want to do? I want to do these mergers. So every time I want to take the two nodes with the smallest possible frequency and merge them together, have a parent that has these two as its children. Okay, and I want to do this until I have only one node remaining. So I say, as long as the size of my heap is more than 1, take the two nodes with the smallest frequency. So I'm going to say, let's say node 1 is the top of my heap, and I have to now pop, I have to remove it. And then I say my second node is again the top of my heap, and I again remove it. That's what happens when you don't read the error codes and you just look at the line that has an error. Okay, so I took the two elements that have the smallest frequency. I'm going to create a parent for them. So I'm going to call this P. It's going to be a new node. P's left child is going to be N1. P's right child is going to be N2. N1's parent is P. N2's parent is P. And P's frequency is going to be N1's frequency plus N2's frequency, right? And now I have to add P to my heap. So I just say h.push. And remember that I have to put P itself here. I have to put minus P's frequency here, right? And that's it. That creates my Huffman tree. I don't have time to write the things that print stuff. But what is my runtime? So looking at this code, it should be easy for you to tell me what my runtime is. So I'm going to start with this heap. And originally, the size of my heap is just the number of different letters that I have. Let's call that n. Let's say I have n letters, right? For every letter, I'm adding one node to my heap. Now, every time I'm taking two nodes out, I'm creating a parent, connecting both of them as children of that parent, and I'm putting this one parent node back. So in every iteration of this while loop, the size of my heap is going down by at least one. I'm removing two elements, I'm pushing one element, right? So this while loop runs for at most n iterations. Now, what do I do in every iteration? In every iteration, I'm asking for the top of my heap twice, but that's constant time. I'm also removing the top element of my heap twice. That's logarithmic time, that's log n. Remember in the heap when we were doing pop, we basically had to do bubble down and all of those things. And then I'm adding some new elements to my heap. And this was also logarithmic time. So I'm spending O log n time in every iteration of this while loop. So my total runtime is O n log n, right? So I can create the optimal prefix-free code in O n log n. Okay, I'll see you next week.